Good morning, ladies and gentlemen. This is the second part of the two-part sessions we have on connecting nanoparticles with carbon reduction. As you know, it's organized partly by Professor Maria Konsta, but she cannot introduce herself, so I'm going to introduce her. So I'm Suru Shah, and Maria is my colleague at University of Texas at Arlington. Among other things, she's also the director of UTC Center. She's also associate director of our Center on Advanced Construction Materials. So Maria, please.
Thank you very much, Professor Shah, for your kind introduction. Always a pleasure to have Professor Shah with us. And when the chief is present, we always give him the floor before anyone else. So it's an honor for me to introduce me to the audience. This is the first presentation of part two of the two sessions that we organized with Professor Konstantin Sobolev for this ACI convention. The title of my talk is, and I think you get a preview from one of the presentations in the first session. Again, I would like to promote the effects of nanomaterials in any aspects of enhancing the properties of concrete, any property, but for this particular session, I'm going to show you parts of our work, how we can engineer the carbonation kinetics so that we can achieve CO2 sequestration, carbon dioxide sequestration. And to highlight this, I'm going to show you two different cases of 1D nanomaterials and 2D nanomaterials. 1D nanomaterials being the carbon nanofibers and carbon nanotubes. They all fall into the same category. And the 2D carbon-based nanomaterials, we consider graphene. In the last presentation, in the previous session, we heard about something that I haven't worked with. It's the 3D graphene, but totally different because we do not know the properties. But for here, I will just show you what this difference in dimensions in the scale we can achieve using these two different nanomaterials. Just a small and very brief overview what we mean at this time, at this point, when we mention the sustainable transition to a net zero concrete. Everything is based on the Paris Treaty. If you all remember that we need to lower the temperature in the environment by 1.5 degrees by 2030. As a means of addressing this, in considering that the construction industry is one of the most pollutant industries, the industry that contributes the most in polluting the environment, and I think Larry gave us a pretty nice overview of that. I will just want to mention here that the tries of the cement industry right now addressing the embodied carbon in concrete construction, obviously due to the cement manufacturing process, comprise of the use of different supplementary cementitious materials, and we've all talked about that, fly ash, slag, metacowling. But for this particular, let's say, times, we would, the cement companies would try to encourage the use of limestone cements. Now, It is to my understanding that limestone cements, they are considered the new type 1. And I have included here many limestone cements, PL3s here, PLCs here, from different companies. Also, I would like to emphasize here that limestone cements are by no means the same from the different companies. So we've seen percentages up to 15% as replacement of the clinker. But right now, these limestone cements have been accepted by almost all the DOTs of the states in this country. So something that arguably will contribute to the net zero, to achieving, or let's say getting closer to the net zero scenario, is using all this supplementary cementitious materials. Some of them are the old ones, like we know. Please note that some of them have started to be produced in a nanoform. For example, liquid fly ash is the fly ash that we know at the nanoscale. But we should really be very careful to see how much this effort will contribute to reducing these emissions. I have included this chart, which I believe Larry and somebody else has already shown, just to iterate here that we have four stages in the production in concrete. We have the production stage here, and then the next stage would be the construction stage, the other stage would be the use stage, and the last one would be the end of life of the construction stage. So the cement companies at this point, they are addressing this first stage. It is our goal in the construction industry and the academia to probably take a look of what we can do at the later stage of a construction in the lifetime of the material that we are all working on, concrete. So right here, we are showing you the direct, the areas that direct air capture, meaning we could use the concrete as a carbon sink, are the areas that we would like to address, as we do not have access to what the cement companies are doing during the manufacturing process. So we are taking the cement ready and we take it from there. But to conclude with this small introduction, please take a look here at this information here, as we are showing what we can do using OPC cement, Portland cement, cementitious, supplementary cementitious materials, and the PLC cement for making concrete. We can lower the emissions by 0.2 equivalent carbon dioxide per cubic yard of concrete. However, to reach the net zero scenario, which would be that zero over here, we need to find somehow this additional 0.5. And how we can do this? Well, this is a very long process to begin with, and apparently we cannot do this using the conventional techniques that we've been using so far. So the theoretical question that we have all in our minds so far is a very simple one. If we can transform this material from a carbon emitter maybe to a net zero emission material, for me, the answer is yes. It's a difficult path. However, we needed to consider out of the box. We need to consider different strategies. We need to engineer the carbonation kinetics. The material can do so much the way it is manufactured with all the inclusions, supplementary cementitious materials, limestone, everything. But we would like to see the carbonation kinetics engineered and an increase in the capacity of concrete in mineralizing the absorbed carbon. Remember that we just talked that we would like to see what concrete can do in directly absorbing the CO2 from the environment and using the material as a carbon sink. So carbon sequestration in concrete is, in general, carbon sequestration is a very slow process, right? Can be a very slow process, and the process depends, at least in concrete, on the carbon dioxide diffusion and the availability of calcium ions. Keep in mind that when we are increasing the amounts of supplementary cementitious materials, we are essentially running a second reaction, which is the pozzolanic reaction, which takes up all the calcium from the cementitious matrix. Now, the carbon mineralization in processing concrete is considered an interfacial controlled process, meaning that this process can benefit from increasing the surface to volume ratio of the solid phases in concrete. But how can we do that? Naturally, we have many amounts, adequate amounts of calcium in the cementitious system that are needed for the mineralization process. However, the supplementary cementitious materials can help us in increasing the surface to volume area, but they are taking up all the calcium in the system. Any process like that involves the consumption of calcium hydroxide, which eventually will lead in a depletion of the calcium in the system. Now, in this slide, I'm showing you simple products of mineralization. So here is a very nice calcium carbonate in cementitious matrix of SEM pictures. And here are all the calcium carbonates that were able to form in a matrix, and this one in particular is with a biochar. What we can do to not only enhance the reaction, but tailor the whole system for accepting more and more and more and accommodating the production of the calcium carbonates. Engineering the carbonation kinetics indeed is a very challenging task, especially when we are trying to use all the conventional approaches. With the proper use of the very rapidly emerging 1D and 2D nanomaterials, maybe I should add the 3D right now that I know. And I'm talking especially about the carbon-based nanomaterials, because there are other nanomaterials, 1D and 2D, which are not yet explored. Now, all these nanomaterials have inherent properties that are unique. Especially for the carbon-based nanomaterials, they have a unique carbon structure, which is extremely helpful in many ways, and obviously, being nanomaterials, extremely high surface area available for surface and interfacial chemistry. this is just a small hint of how we can increase significantly with the surface to volume ratio of the volume of the solid phases inside concrete by using tiny amounts. Usually, these amounts are less than 0.5% of the weight of the cementitious materials that we are using. So, in this slide, I have included also the specific surface area of the carbon nanotubes here, but take a look at the specific surface area of the 2D nanomaterials. Look at that. Did you see the difference? Extremely, let's say, not only their structure is different, the specific surface area is sixfold higher, and considering the, let's say comparing with the surface area of the Portland cement and the supplementary cementitious materials, you can imagine how the proper use of nanomaterials inside the cementitious matrix can alter the nanostructure and enhance the, has a significant effect on the acceleration of carbonation kinetics in almost any cementitious system. Now, I'm going to start with showing you some results from carbonation using carbon nanotubes in the beginning in the system, and then I will switch to graphene, the 2D nanomaterials. Dr. Danoglidis mentioned before that we are using a specific technique, a regime for carbonation. In this particular experiments, we used carbonation for 7 days in an environment, in a carbonation chamber with 12% carbon dioxide concentration and 65% relative humidity at 74 degrees, and again, this is a regime that simulates the CO2 sequestration capacity of concrete when it is exposed to outdoor conditions in metropolitan areas like DFW, for example, where there are carbon dioxide particles in a concentration of 400 to 430 parts per million. And this process is simulating the exposure for almost 3 years. And this is according to a RILEM source. Now, from the TGA graph that I'm showing you here in the right part of this slide, we observe that the consumption of calcium hydroxide in these specimens, and these are considered 10-day specimens. Remember, we have 3 days moist curing, pre-curing, conventionally curing, and then we are adding for 7 days carbonation. So for this 10-day carbonated specimens, we observe that the consumption of calcium hydroxide increases by 20% when we are adding to the system carbon nanotubes right here. Honestly, I didn't think that this was the best that we could do. Perhaps maybe I was too ambitious in that. If we examined a little bit further and see what we are doing, how we are doing it, measured the mineralization here, 17% increased the CO2 mineralization. In concrete, we added experiments with specimens that were outdoors, right outside our lab. This is pretty consistent for the environment that we are talking about. Now, this process is considered, it is also known as a process of a dehydroxylation of the calcium hydroxide. we would like to think that an enhanced dehydroxylation would naturally lead to an enhanced mineralization, right? But again, we were not satisfied using these results. So we decided to add one of the recommendations that the cement industry is giving us, adding a little bit of supplementary cementitious materials, fly ash, in the system, and this is fly ash class C. The reason that we wanted to use specifically class C is because we wanted to to add a little bit of calcium. We did not want the pozzolanic reaction to take up all the calcium, and we wanted the mineralization process to increase. Now, if you compare the calcium, the carbonation of an OPC system with an OPC plus fly ash here, you will notice that we do not see that much difference. 17% here, 17% there. So fly ash, I mean, does not alter our system. We did not have the results that we were hoping we would. Adding CNTs, though, made a difference here. But again, the difference that we see between the two systems, the OPC systems with nanotubes and the OPC systems with the fly ash, I think it contributes, but again, it was beyond my expectations, as my expectations continued to be very ambitious, and I strongly believe in the properties of the nanomaterials. Forgot if I mentioned that we substitute 30% of fly ash in the system. And again, the amounts of carbon nanotubes that we use in the mix are tiny. It's barely 0.1% per weight of cement. Everything else remains the same. Carbonation regime the same, like the one I showed you before. And here are the results that we can consider adding fly ash, adding carbon nanotubes. We probably managed to make a little step, a baby step towards the net zero scenario. Much better, though. You have to agree that much better. Carbon nanotubes help. Now, what happens if we switch a nanomaterial? We can move from 1D to 2D. Now, these pictures are from our AFM. This picture, the first picture here at 200 nanometers shows clearly the structure of CSH with a very nice carbon nanotube. Right here, the highlighted part here is the lighter part is a carbon nanotube. Now, next picture here shows graphene nanoparticles. This particular graphene that is shown in the picture is a three-layer graphene. Graphenes rarely come in a three-layer or monolayer form. They come in stacks of at least 20 or 30 layers. Again, this is the same scale, 200 nanometers, but look at the interface between carbon nanotube and CSH at 10 nanometers. And by the way, the interface here, this part here that's considered the interface between the two materials has a width of 2 nanometers only. And here is the interface of the graphene platelets in the cementitious matrix. Now here we do not have a very clear picture of the interface, but you can see the contours of the three layers of graphene. The reason I'm showing this to you is this carbon nanotube here, the specific surface area is 150. And the specific surface area of the 2D nanomaterial graphene is, again, 5 times higher. So consider if the difference that the homogeneous distribution of these two materials in the cementitious matrix, the difference in the surface to volume area can have. Now, our AFM system is equipped with a nano-IR system that allows us to conduct a chemical property mapping at the interfaces. So we can go down almost to the atomic scale. And this is what I would like to show you here. This is the same picture that I used in my previous slide. So this will give you an idea of the FTIR, nano-IR at the nanoscale, FTIR at the nanoscale of the CSH. And then I will move to show you what happens at the interface. So this is, I'm showing you the nano-IR spectra of the CSH. In this spectra, there are two typical peaks that we find in general, and I'm talking about carbonated specimens all the time. So the peaks at 1370 and 870 show the presence of the carbonates right here. I cannot, that's where it's the other one. It should be right here, right. Now you see that there are a few in the middle. These few in the middle are not associated with the carbonates, but these are silicon oxide peaks, 1140, 1060, 980. And they generally show the silicon oxide bonds associated with the CSH structure. Now, what happens if we move to the interface here between the graphenes and the CSH? This area here that, again, has a width of 2 nanometers. Now, look at the peaks here. The calcium carbonate peaks here. See, everything is increased. Change in intensity, which is a huge, actually, change in intensity. Now, not only the carbonates, though, but we see also a change in intensity of the silicon-oxygen bonds. Why? You will probably wondering, because we were wondering ourselves. Now, the silicon-oxygen bonds are 3, 1, 2, 3, 1, 2, 3, but, and we have an increase in intensity of the two, but one of them is going down. Now, this is actually a pattern that is pretty typical during carbonization. It appears when CSH undergoes the so-called polymerization due to the consumption of the calcium from the system. This process is also known as decalcification of the CSH. Why the CSH is being decalcified? Because apparently this calcium coming from the CSH here react with the additional carbon dioxide to form additional carbonates. Now, this is why we see not only these two peaks enhanced, but also the carbonates here, the intensity of the carbonate peaks is a testament that at the area of the interfaces between the graphene's significant surface area and CSH is extremely high. Significant amounts of carbonates are able to form specifically, preferentially, at the interfaces, and this greatly enhances the mineralization capacity of the graphene-reinforced concrete. We used some fly ash, if you remember, from our experiments with CNT, with carbon nanotubes. We added 30% of fly ash in the system. Here are the results. Remember how disappointed I was before when I was telling you that I saw only 17% of enhancement in the calcium carbonate percent from the TGA. Look at the difference now. Now we managed to increase this at 66%. So if we want to compare the mineralization process phenomena that take place when we have fly ash mixes, and we want to compare the performance of carbon nanotubes and graphene. Remember the difference in the specific surface area. We observe that this significantly enhanced surface area that we have through the addition of graphene nanoplatelets when compared to the CNTs results to a production of a much higher amount of carbonates. Therefore, it significantly enhances the capability of the cementitious system for mineralization. And though carbon nanotubes can do a wonderful job, graphene outperforms the 1D structure materials due to its unique 2D structure. I just want to think of the next generation of 3D materials, which I'm not familiar with again. If you want to see how this translates with respect to our net zero scenario, yeah, the GNPs made the difference and we managed to go beyond the zero. This is an additional 0.2 to 0.1% that contributes to beyond a net zero concrete material. To be consistent with all the work that we are doing, we examined the mechanical property, we ran the mechanical property tests for all mixes in this work. Very briefly, we are very well aware that carbonation increases the brittleness of all cementitious materials. Of course, this is accompanied with loss in ductility. Both phenomena are together. Look at what happens in the mechanical properties, though, when we increase carbon nanotubes and graphene. Not only we have an enhancement in the mineralization capacity by offering additional sites for carbonation reactions, it is due to their unique mechanical properties, modulus of elasticity of 1 terapascal, etc., that contribute to reinforcing the cementitious matrix at the nanoscale, and we see phenomena like prolonging the proportionality of stress to strain and enhance the tensile load-bearing capacity, also the strain energy absorption capacity at the post-cracking stage of the formation. And with that, I would like to conclude this presentation. I'm giving you an overview here for the direct emissions that, as calculated, the metrics is the equivalent from to compare the emissions from various greenhouse gases on the basis of their global warming potential. Clearly, nanoengineering the material is the way to go if we want to do a modification in the carbonation kinetics. Thank you very much.